Welcome.
Yeah, thank you. My name is Joachim Breitner. I recently joined the Defini Foundation, which is one of those blockchains. If you want jobs, look there. I'm not going to talk about the company. I'm talking about other stuff that I've been doing previously. And I want to start with an anecdote. An anecdote begins about a year ago, not far from here in Bristol. Bristol had this workshop, IFL, Implementation of Functional Languages, and Matthew Pickering gave a talk on generic lens. Now, this isn't Matthew Pickering, this is Tonga Kist, and this isn't IFL, this is ICFP, but it's the best picture I could find. Because he's not talking about generic lens, so it's not completely bogus. And generic lens is a cool library. So I think this room is half empty because I marked this as an expert talk, but maybe at least I can, it allows me. I think they ran, okay. Okay. Generic lens is a library. It's about lenses. And I will not make this into a lens tutorial, but I'll give you a very brief idea what a lens is. So let's say we have a data type. It has fields. Then instead of always writing the code that reads and, is the audio okay? Okay. Always write the code that goes into the data type, modifies the field, and come back. What you can do with a lens is you have this one value of type lens, and it's an abstraction over the idea of a field in a data type. And you define this lens thing once, and you can use it for all kinds of things like reading the value, setting the value, modifying the value in a monadic context. So it's a super useful abstraction. People that deal with big data types use it a lot. Who here uses lens of some? Okay, I can stop talking, I guess. I guess most of you use it, and the other probably have a rough idea what it is. The point I'm trying to make here is, well, if you want to have a lens, you have to write this boilerplate code. Who of you writes boiler lenses by hand? Oh, no, okay, I didn't expect any hands to go up. I guess most of you will probably do something like this, right? You use template Haskell. Template Haskell is this meta-programming language that at compile time creates the syntax of the code that you didn't want to write yourself. And that's fine and good and gives you the stuff you need. But some people don't like template Haskell. Because, for example, you need to, like if you want the lens to be named age, you have to rename the field, and that's a bit annoying. And then with template Haskell, you don't know what precisely is being produced. It's a bit opaque. It doesn't go well with cross-compiling. So using lenses but not using template Haskell, well, that's what Matthew Pickering made possible by creating this generic lens library. It allows you to just write, so you don't have to modify the data type at all. Oh, I guess yeah. There should be a deriving generic at the end. I dropped that for some reason. But you don't have to modify the data type at all. And whenever you need a lens into a field age, you just write field at age. And then generic lens uses this very advanced machinery, using everything that THC has created in the last decade to give you this lens out of thin air. And it does so using basically two main features. One is generics. So generics means that given you have your concrete data type, here your employee, but then GHG also knows how to turn it into a generic data type. Generic means it's built out of a very small number of building blocks. Products, sums, constants. So in this case, to make it more concrete, you can think of employee being isomorphic to the tuple of string and int. And if you had just tuple and string and int, you could imagine, okay, now I can write code that just deals with tuples, generic code. And once I convert this into a tuple, I can use my generic code and do whatever stuff I need to do. I think this mic is this mic okay?
Yes.
Okay, it sounds strange here for some reason. Sorry. Okay, so what generic lens is doing, if you build this lens to get the age field in this data type, is it takes the concrete type, employee, converts it to the generic representation. So it's like a tree of sums and products. And then it uses type-level computation, type families, type classes, all the fancy stuff, to go down this generic tree or this generic data type, find the the field that you're looking at, specified here by its name, but you can also specify it by type or by position, does the kind of lengthy stuff you need to do, and converts the generic data type back to the employee. And I read about this on Reddit, and then I went to IFL and heard the talk, and I was very amazed by this. This is what Haskell is about. We have these abstractions that allow us to do very high-level programming, and we have these advanced features that give us these abstractions very, very easily and very convenient. And it's putting all these fancy features to use. So I was very fond of this work, but I wouldn't use it. Can anybody guess why I would not want to use it in my real code? Wild guesses are welcome. Just shout it in. Second? I kind of believe what it's doing. I mean, I can test it and also type. I mean, the type of a lens actually prevents you from doing anything else than being a lens of this type in this field. So the type check already does a lot of checking it. But somebody else said it's slow. Yeah. I mean, this is a small data type, but imagine you have a big data type. And you convert this big data type, lots of fields, lots of nesting, into a generic representation all the way down. And then you traverse it, and you change things, and you convert it all the way back. This can't be efficient. So at the end of the talk, I asked, so Matthew, how expensive is it? And he said, oh, it's free. The compiler optimizes it all the way. Now, I happen to be a GHG contributor, so I believe I know a little bit about what GHG is doing. And I did not believe that. So I looked at the paper that they wrote. This was the paper in the pre-proceedings for IFL, not the ICFP paper, but the content is the same. And there they write in the conclusion, the confidence that the abstraction will be without cost. It's a pretty bold statement. So I looked at the paper, how they came to this conclusion. Well, and what they did is they created a module. And it looks like this. And is this large enough in the back? Should it be larger? OK, great. They created a module that has the generic lens and also the manual lens. And then they compiled this module with optimizations on and asked GHG, please tell me the intermediate code. What did you do with this after optimization? And they compared the manual and the generic version, and it looked the same. And therefore, if GHG optimizes both variants to the same code, then it's pretty plausible that there's no cost involved because they are the same at some point in the pipeline. That's a pretty compelling argument. I still didn't believe it. So I tried it out. So a little time travel. This is 8.2. We are compiling with optimization the file example.hs. And we're using the generic lens library from that time, which is 0.4.0.0. And then we also, let's see, we asked the compiler to dump simple, which is print the simplified code. And because otherwise the output would be very big, we also need to suppress a few things. And then we can pipe the output to less and look at it. So this is what GHG does to this module. This GHG core, it's like this elaborated form as Haskell with explicit type annotations and explicit type lambdas and all kinds of stuff. And we can look for the code for the manual version. It's up there. OK, that looks reasonable, similar to what we wrote before. And then below is the generic version. So this is how it begins. And then we can start scrolling. And scrolling some more. Maybe I should scroll by pages. OK, I'm scrolling whole pages. Still the generic code. And, oh, there was lambda. That was interesting. OK. And that's done. That is not the same code. I was right. So I went to said, hey, Matthew, how can you claim all these things? Look at this example. It doesn't work. And then Matthew said, I don't know. When I tried it, it worked. Tsongo, what did you do to the code? And then Tsongo said, oh, let me have a look. Oh, yes, I found it. Here's the problem. And he released half an hour later version 0.4.0.1. And if we now look for the manual code, we find it there. And if we look for the generic code, we find it there. So not only did GHG optimize both codes to the same code, it even detected that they are the same and made one an alias for the other. This is the common sub-expression elimination optimization. OK. So now I'm convinced that it's the same code. So their promise that they made, the generic code will be just as sufficient as the manual code, is true in 4.0.0.1, not in 4.0.0.0. So somewhere something went wrong. And this brings me to the main topic of the talk. Something went wrong. And this is not a singular instance of this problem that we have. Here's another example. I guess many of you have seen this file. It's a documentation for data text library that probably, yes.
How big was the fix?
I think it was just eta expanding some function because GHG inlines things differently depending on how many arguments you have, manifest and something that should have been inline didn't inline, and then the optimization stuff didn't happen. Okay, I guess many of you have worked with data text. It's like the library to use when you deal with text. And part of this module is this following documentation section, which claims that in this case, text fusion happens. If you write a function that is in the position of functions that produce text, then GHG will optimize that into one big thing where the intermediate value will not even have to be created. So this code here takes in a byte string, returns an int, and there are two intermediate values superficially, but claims that the compiler will optimize it away. It'll just be one function that loops over the input byte string. And these kind of optimizations is what make me proud as a Haskell user. This is like these large-scale things you probably can't even do in a language that is not pure and not functional. And I give them as examples of why Haskell is great, and people that work on other programming languages are like, really, you can do that? But this is not true. If you try this, if you put precisely this code all from the documentation into a file and compile it, and you look at it closely, and I'll skip it for interest of time, so you have to believe me, then there will be one intermediate value of text there. So one will be fused, one will stay there, somewhere something went wrong. So it's again the same pattern. A library makes a promise to this user, but doesn't hold it. So why are these promises so hard? Libraries make other promises. You know, like data set promises that it implements a set. And there's no bug there. That really is a set. We actually proved that in a different project. There are no bugs in containers. So why are these bugs there? Well, because these are promises of a non-functional nature. In both of these cases, if they go wrong, you don't see it in the running code. You can't observe it by writing test cases the way you usually would. Your program will still do its job just fine. Maybe slower, maybe more memory, maybe something else is wrong. But you don't see it just by looking at the behavior of the code. And this brings me to this term inspection testing that you see in the title, which is my attempt of giving this problem a name so that people can think about it and realize it's something that deal with and improve the situation. So because it replaces what you do when you manually inspect the intermediate code. I call it inspection testing. It's the best we could have come up with. And I'm trying to give it a precise definition to make it clear what it is not. So inspection testing is when a non-functional property of a compilation artifact of a specific piece of code is specified declaratively by the programmer and checked during compilation by the compiler. Let me break that down. So I already mentioned it's a non-functional property. That's an odd color. Different color here. It's a non-functional property, meaning that it's something you can't observe in the behavior of the program. If you could observe it in the behavior of the program, you can just use HUnit or quick check, and we have great tools for that. it should be a property of a compilation artifact, and not, like, compilation artifact would be the intermediate language or the resulting assembly or the machine code that comes out at the end, but not of the source code. We have checkers for source code, HLint or others, liquid Haskell, other checkers, and that's not a new problem there. And it should be a property of a specific piece of code, in contrast to all the code you can write. For example, a language like Haskell has a promise of type safety, meaning that all programs will not crash unless you use unsafe features. But that's something that we, at least theoretically, prove about the system. We don't need to test it, it's proven. Or for example, a C program, if you compile C code, you get the guarantee at the end by the linker that there are no unresolved symbols anymore. That's something that the linker just checks for you. You don't need to test it separately. So we're looking at properties of a specific class of functions, like the text pipelines, this fusion of text functions, or the generic lenses. And we're looking for properties that are specified, because you might see that Haskell programmers, advanced Haskell programmers that care about performance, they will compile their code with THC and look at the core, and they will like skim through it and say, that looks reasonable, nothing fishy here. That's useful. I encourage you to do that. But you can't automate that. That's too much gut feeling. So we need to make the author to think about, OK, what am I actually looking for? How do I detect that fusion has happened? And once they can describe what they want to look for, we want to give them a way of describing it declaratively, rather than just having to implement a complete new analysis that traverses the AST. And I mean, you can, yeah, it should be easy to use. And you'll see later what that means. And it needs to be checked. It is already useful without being checking. And we see that in the text code. So if you look at the documentation again, it says here, functions that can be fused by the compiler with the phrase subject to fusion. And if we look here for subject to fusion, there are 47 functions in this file that are supposedly subject to fusion. And this is a declarative specification of a property, but it's not being checked. So in order to make this, we need to check it. And then finally, it should be checked by the compiler, because we care about what the compiler does with your actual code that you want to run, and not what some other tool might be able to do with it. OK, this was a bit dry, so let's get a bit more concrete. What could this be? What kind of properties might we want to look for? And we've seen the first is basically the example from the first slide. We have two pieces of code, like one low-level handwritten code and some high-level stuff that should optimize the same way as the low-level code or to the low-level code. So we want to ask for that. In some cases, maybe we don't care about all the details. Maybe the type annotations may be different. So it's just some equivalence that we can ask for. And we've seen the elimination of intermediate data structures in Fusion, where we want to assert that certain types don't no longer appear, maybe. Another popular request that comes here with Haskell is, I'm using all these type classes, and I've heard these stories about type classes being dictionaries that are being parsed that contain function pointers that are indirect calls, which surely can't be fast. And hopefully, at the end of my optimization, all the type class overloading has disappeared, and GHC has inlined all the dictionaries, and all the code is just direct function calls and fast. And this is something many people hope for, but maybe they want to test it if they have a reason to assume that it would happen. Similarly, if you write high-efficient Haskell code, and maybe you've seen the talk, the previous talk in Alt-Tab, in one of the rooms downstairs just right now, you care about whether your code is allocating stuff on the heap. And a tight inner loop that's fast ideally doesn't require any heap allocations. And that's a non-functional property that you might want to test for. And it's not just performance. I mean, most of them indeed are performance motivated. But if you think about security relevant code, what you want there often is that there's no branching in the code, or at least no dynamic branching that depends on the secret values, because then you have a side channel attack, and an attacker can get the secret value out of your code. And in this case, you want to check that there is no branching. And if you have more ideas, I'm happy to hear them. So how could this look in Haskell? Well, let's go to our code, and let's do some wishful thinking. In an ideal world, maybe there would be integrated compiler support for this kind of stuff, and we could just enable a language extension called, I don't know, inspection testing maybe. And then we maybe get a new top-level declaration form, a command, so to say, that we can tell the compiler, please inspect the code and tell us if the manual lens is the same as the generic lens. That would be nice to have, wouldn't it? Now, this would require changing the compiler. OK, I happen to hack on the compiler sometimes, but you would only benefit if I can actually convince Simon to put this into the compiler, and this is like this strange new feature, so maybe not. And then maybe I would have to have my fork of the compiler, but none of you would install a fork just for this feature, so this would be bad. So what is the next best thing we can do? Well, we can try to extend the compiler, but there's not really a way of extending the syntax of Haskell at the moment. I mean, we've seen an influx of new plugin styles for THC, but still there's no plugin that actually extends the parser. So we can't really add a top-level command. But we can fake it. And the way to fake it is to use template Haskell. So I have a producer library called inspection testing. And if we import test inspection, we get function inspect. And we can just use it like this. And now it looks like syntax. It's really just a template Haskell splice. The only change I also have to make is to add quotes in front of the names, because that's how you refer to names in template Haskell. Because I don't want to, yeah. So we're pretty close to the syntax that I would be hoping for. And now I can compile this. And I no longer need to dump the simple, sorry, because well, we don't want to look at it manually anymore. And if I compile this, no error message, everything's fine. Great, isn't it? So let's try the old version. Also no output. Something went wrong. This is like a test to see if you're still awake. I mean, I'm just extending the syntax. I haven't yet extended the behavior of the compiler. And the way I do that is with a core-to-core plugin. So the thing that we want to check for is a property of the core code. And luckily, GHG provides an interface for libraries that modify the core code. It's meant for adding optimizations. But we can abuse it to just look at the core and then just kill the compiler if things go wrong. But we have to load it. If you don't load it, nothing happens. So we have to say, please use the plugin test inspection plugin. And now if we compile it with the fixed version, it says, yay, here's my plugin, suddenly appears and says, I found this obligation, and I checked it for you, and it looks good. OK, let's cross-check what happens if we do the old version. And if we do the old version, then it'll find the obligation, find the left-hand side and the right-hand side, the two versions, and it'll tell me, yeah, this failed. This is the left-hand side, and this is the right-hand side, and they're not the same. So now we can do what we did manually automatically. And this means now that, and the generic lens people started using my library and put it in test suite, and they wanted to support multiple versions of THC. And it turns out that even though they fixed this one bug in 0.4.0.1, if you compile this with GHG 8.0, it failed. And now that they had the automation, they could test this easily. It just Travis checks all supported versions of GHG, whether all these optimizations still work. And now checking these things becomes really quick. And we can just, well, now they found the problem, and they can fix it. And now it works with the old version. And it works with GHG 8.2, and it works with 8.4. And it's suddenly much more efficient to check these things. I'm going fast. OK. Okay, what am I missing? Right. So what else can this library now do? So maybe it's actually nice to show the headoc. It's more believable. So inspection testing is now a library that you can use. Just install it. Supports GHG from 8.0 upwards. And you can check for various things, namely, well, it's a subset of the thing we just discussed. We can ask for equality between two functions. We can ask for the absence of certain types, which is useful for the text example. We can check with function takes no allocations, and then we do this thing where we can check whether certain or all type classes have been completely eliminated from the code. And you just, like you've seen in the code, like here, you import it, you don't forget to load the plugin, and then you just put in your inspection tests. And we see that the generic lens people are now doing this. This is, I hope it's still there. This is a master, but yeah, here, this is a test suite. They're loading the plugin, and then they have all kinds of manual and automatically derived lenses. And somewhere at the end, I assume, yeah, they have their tests. And this now scales. And the scaling is important. So we've made it fast enough with inspection testing to replace, like, okay, here's one example, like a unit test, so to say. We replace looking at manually with this little automated test, and we can easily scale it now to different versions of GHG or different versions of depending libraries. But we can scale it even more. So if we remember this example, data text, where we have where we have 47 functions that are subject to fusion. We've already seen one example where it wouldn't fuse properly. But doing, like, we can test this, like, this is how we can test it in one step. So, and I think I have something prepared. So here's the pipeline that we've seen, and here's two more pipelines that we can check to learn more about it, and then we can write some kind of tests. And I also need to, of course, load the plugin. So let me copy this into this file, and also the import. OK. So we have 3 such pipelines of text functions, and then we test that this one and this one, the text type is completely eliminated. And we also test whether it has been eliminated in the count characters, and we tell the system, I'm expecting this to fail, so it won't just fill up my my screen with a dump. And we can compile this. And yeah, it correctly finds that 2 of these succeed and 1 fails. So this works nicely for 3 examples, but we have 47 functions that we want to test fusion. And then the question is, okay, fusion is a property not really of just one function, it's a property of 2 functions. And maybe 2 upper fuses usually, but not if you combine it with 2 lower. So really, we want to test combinations of these functions. So now we are at 47 times 47 examples, and really, we don't want to write this all down. But we don't have to, because this library happens to be using template Haskell to specify the tests, and template Haskell is just all of Haskell as your meta language. We can just use template Haskell to create many, many tests. And that's what I did. So let me, just so you believe it, remove the stuff that's being compiled. So this is a little project that I wrote where I'm generating random pipelines of text functions. And let's see, some of these, I guess this is now taking a lot of time because it's now actually doing all these tests. And what it does is for each of the functions in text API, which is supposed to be fusing, it's creating an an example pipeline together with other functions that we expect to be not problematic. And then we get an output like this. So this says that, OK, the pack function is documented to fuse. That's the first tick. And it actually fuses. That's the last tick. And ignore the second tick. But then unpack CS string is supposed to be fusing, but it doesn't. So here you find the first example. And reverse is supposed to be fusing and doesn't, and so on. And then we not only look at each of these functions individually, together with in a pipeline of nice other functions, we also just randomly generate pipelines of various lengths, of various functions, just what you would do in QuickCheck, just throw randomness at it. And this is just the fast version for the talk. I ran this with 1,000 pipelines just to make sure that I get a good coverage, but this would take too long for the talk. And scaling it up this way yielded the following result. Data text has 11 functions that are supposed to be fusing but don't. It also has 2 functions that's at the bottom, sorry, that are not documented to fuse, but they do fuse. That's a happy result. We just need to fix the documentation to make bolder claims. That's good. And then because it's automated, we can easily scale it to data text.lazy, which is the same API more or less, but a whole new set of functions and a different set of functions that where the documentation don't matches whether it fuses. So we can take inspection testing as a testing paradigm, and we can apply all the ideas that we have from normal testing, such as, in this case, property-based testing, and get even more coverage. And right. So this is now a year old, the library. I'm happy that a few people are picking it up, in particular the generic lens people, but also Oleg, who just gave a talk here before me in this room, I think. And more people mostly doing stuff with generics. So if you find yourself writing a library or writing code for anybody, and you're making these kind of promises about how your code is optimizing, how your code is being optimized by GHC, then maybe you should pause for a moment and think, well, how can I make sure that whatever I'm claiming right now will be true next week after I've upgraded GHC, after I've modified the code, after I've upgraded the library. And well, hopefully you'll start using inspection testing and also spread the word to all the other languages who can benefit from this. We might be the first to have this, but I think essentially all high-level languages will have the problem. And yeah, with that, I'm happy to take lots of questions. Yeah, Duncan.
So about the fusion, are you sure that this is the absence of the type check is a sufficient condition?
Good. That's a good point. Yeah. A problem with the approach is you have to somehow specify your intent, and the intent fusion happens is a bit vague. Like, what does it precisely mean? The best I could come up with as and I agree it's an approximation that. In the compiled code, the type no longer appears as the type of a parameter or lambda bound thing or a return value, and this is what I'm checking. And I wouldn't be surprised if this could be refined. But I'm fairly certain that it's at least indicative of the problem that we want. So if I look at the core for this example, I see that there's a text value being allocated, and I believe that shouldn't be the case. Yeah. For example, if you have the function search, it takes 2 text parameters, one for the needle and one for the haystack. And presumably the fusion only applies to the haystack, not the needle. So even if fusion happens, the needle stays around. And I'm excluding these kind of functions from my tests. So if you look at the code for this then I have a bunch of functions where I don't know how to test them because that type doesn't really fit this pipeline stuff easily. And then I have And the other functions are categorized in producers, so they functions from a non-text text type to a text type, and then transformers to text, and then consumers which consume the text. So I'm only testing the subset that fits this bill, but I think none of the functions that I categorize as untestable is actually listed as should fuse. So yeah, there might be false positives still. Maybe I got something wrong. But I'm fairly sure that the overall result is true, that text fusion does not apply as reliable as we would hope for. Okay, Duncan. I guess you have a personal stake in this.
I don't know if okay, there we go. So here's a concrete suggestion of another bit that would help to ensure that fusion is happening. Right. So one is, as you said, that the type no longer exists. But if you look at how this particular type of fusion works, which is stream fusion in this case, that's not enough. You do need another thing, which is at least you also need to know that these intermediate constructors in the stream are gone. So but that's exactly another thing that you could probably do. I didn't see that in the list of your things that you can check. Is that one of the things? Can we check that these three constructors do not appear in the syntax?
Yeah, we could add that easily. It's currently not supported by the library, but I don't think there's reason not to. It might be more or less equivalent to saying that the type that these constructors produce no longer appears.
Maybe.
Or not equivalent, but maybe usable. But I guess you're right. So, but we can check this. We can remove the this.
Yeah, I guess that's right. You want to check that all three constructors of the stream type do not exist. So yeah, that would be equivalent, I think, to the stream type itself not existing.
Do you remember what the name of the constructors are?
Next, skip, and done, I think.
Okay, interesting. They. Oh yeah, there's skip.
There we go.
Okay, so maybe it would fit here as well.
Oh, yield. Yeah, there we go. Sorry, not next.
Okay. Yeah, I guess I should add that. I guess I should just also add just like a simple core to bool thing so that people can write their own little tests before they officially get merged into the library. Yeah. Thank you.
Any more questions? No? Well, thank you very much.
Well, you're welcome.